Hello and welcome to the first video of this playlist. This is video 1. This is not the first video. We had a video 0 before this, where we introduced the logistics of the course and a brief introduction to social choice theory. We have not really gone into the book yet. With this video, begin to go into the book. Now, I do hope that before you watch this video, you have read chapter 1 and 1 star. We will obviously be dealing with the starred chapters, which are the mathematical chapters. We will discuss, while doing that, whatever is written in the conceptual chapters, the non-starred ordinary chapters as well. So the first chapter is essentially to do with preference relations. Of course, we know the mathematical notion of relations. We will be dealing with preference relations here, defining in general what such relations will look like. We will delve into certain properties. One thing I must state right at the beginning here, that the difference between individual preference relations, right, which are R1, R2, and Rn, one relation for each individual, and social preference relations, which is what we usually call R. This difference is irrelevant in this chapter, right? Because we are just studying preference relations in general, defining certain things about them, certain properties which they may have, deriving certain lemmas and theorems, etc. Right? So we can ignore this difference for the meanwhile before we head. Okay. So, what are preference relations? Now, in general, we know what are relations, right? A relation, like your part, a relation on, say, a set S, right? This is a definition. Is a subset of S cross S, right? So let's say S is a set A, comma. Then S cross S is the Cartesian product of S with itself. This is the set, right? And this will be the Cartesian product, right? Now a subset of this will be a relation. So let's define a relation R as A comma A and B comma B. This is a relation R. This is a subset of this, which you can clearly see, right? This is one way in which we look at relations. Another way to look at relations, right? This is one way. This is way one, which is the traditional mathematical way in which we do relations and functions as well later on. The second way, which we will use for social choice theory, let me call the screen for this. Instead of defining this relation like this, we will define R is a relation of S, right? A R A and B R B, which is to say that A is related to R using by R and B is related to B using R, and hence these are the two elements of R in a sense, right? So instead of defining this this subset, we will just say this, and by extension, right, we can say that ARB is not true. How do we show this? We use this symbol and we write this. So ARB is not true. ARA is also true. Right? So this is what a relation is, and we will be using this notion which I defined here. Now, for preference relations, so now we have the set of social states S. Right? S is the set of social states, right? And a preference relation in our context will be a relation, a preference relation on S, right? We will call it R, right? Of course, when it's individual and social, there will be different notations which we will explore later on. So S cross S, right, will be the tuples of social states, right? So if we say, let's say x comma y belong to S. If we say x r y, right, what does it mean? It's the same as saying x comma y belongs to the set R, which is a subset of S cross S, as we have already shown. What this means is, so x r y is the same as saying x is at least as good as y, right? I think this is very clear, right? So we can also have x r y and y r x, for instance. So x is at least as good as y, and y is at least as good as r. That will lead to us saying that the person is indifferent between. We will come to that in a while. Of course, this notion I have used this for the final time here. I don't think we will require it any further. I will only be writing x r y, etc. Okay. So this is what a preference relation essentially looks like. Moving on. Right. So the book tells us that certain properties which can exist of preference relations, right, which may exist. So there's no hard and fast rule. It depends on how you define the preference relation, but these are certain properties that may exist. The first is reflexivity. Right? What is this property? It means that the preference relation R is such that for all x belonging to S, we have x R x, right? Which means x is at least as good as itself, right? And I think the book says that this is not a property; this is a condition of sanity. So if you want to remember it like that, I think you might as well. The next property is completeness. Completeness means essentially that for S, any two elements in S, say X and Y, a comparison can be made. Right? So it's not that under this preference relation, society, individual, whatever, cannot make a comparison at all. So for all X comma Y belongs to S, right, such that X not equal to Y, so there are obviously different elements. X R Y or Y R X, right? So X R Y or Y R X. So at least one of these two, at least one must be true. Both can also be true. Another way to state this is, and this will be useful for proofs, another way to state this is not X R Y. So if X R Y is not true, it means Y R X must be true. Because otherwise, if both are not true, it means you can't make a comparison. Right? So these are two properties. We'll look at a few more. Property number 3, transitivity. So for all X, Y, and Z belonging to S, we should have, right, if X are Y and Y are Z, right, this implies X are Z. So if X is at least as good as Y and Y is at least as good as Z, then X is also at least as good as Z. Okay? This is another property that you may have, you may not have, right? But this does look like the sort of property you want your preference relation to have. Again, we will explore these themes of wanting these properties later on. The next is anti-symmetry. Anti-symmetry. Anti-symmetry says that for all X comma Y, right, belonging to S, we will have, if X are Y, right, and Y are X is true. So if you have this symmetry, X are Y and Y are X, That means x and y must be the same element. The next one is also to do with symmetry. It is called asymmetry. I'm not writing for all x again. It's repetitive. So x r y implies y r x is not true. Right? So if x is at least as good as y, so when we say at least as good as it means it may be equally good or it may be better. That is what at least as good as. So here it says if x is at least as good as y, then y cannot be at least as good as x. So if x is at least as good as y, that is equivalent to saying x is better than y. It cannot be equally good. All right, and the last property is that of symmetry, which is the exact opposite of asymmetry. X r y implies y r x. All right. Okay, so these are 6 properties of reference relations that might exist. Right? Now let me explain a little bit about the symmetric and asymmetric components of a preference relation. It's very relevant at this point to understand, because otherwise those properties may not seem very useful to you. Okay, so x r y means x at least as good as y, right? Now at least as good can have 2 meanings. The first meaning is equally good, right? So for instance, we say this is not preference relation in general, right? We can write 5 is greater than equal to 5, right? 5 is at least as big as 5 because they are equal. So it's at least as big. The second thing is better, right? So 6 is greater than equal to 5 is also true, right? So now this is called the asymmetric, this is called the symmetric component of R. Symmetric component of R. This is called the asymmetric component of R. Why is it so? Right? So here we define a new relation. We define a relation P. What is P? How is P defined? X P Y. Right? If and only if X R Y and not Y. So X is at least as good as Y, but Y is not at least as good as X. So obviously Y is worse than X. And from here we know X is at least as good as Y. So X must be better than Y, right? So this is actually, this notion is X better than Y, right? Which is this. This is called the asymmetric component. And another relation we define is I. X I Y means X R Y and Y R X. Right? X is equally good as Y. Right? Here P means prefers and I means indifferent. So XPY can be read as X preferred over Y. So it's strictly better. XIY is X indifferent to Y. And XRY subsumes both of them based on whether the opposite is true or not. Right? So here you'll be able to make sense of certain properties. So reflexivity, for instance, XRX, right? XRX, for instance, right? Obviously, intuitively, you would think that X is indifferent to X. Again, a condition of sanity. So I can write this XRX and XRX. Therefore, XIX. For instance, right? Another thing may be asymmetry. What does asymmetry say? It says XRY implies not YRX. Can I write this whole thing as being equivalent to XRY implies XPY? Yes, because XRY implies this, but this and this together implies P. Symmetry. XRY implies YRX. So this is the same as saying that XRY implies XIY. Right? This is something for you to think about. All right. Moving on. Right. Moving on to the next topic. I hope that we are clear till now. If it's not, I think I suggest you go back, rewatch the video, try to work it out by hand, read the book, do some exercises, and I think it will be fairly clear to you. Right? Now we will define two new things which are very, very important, as we will find out later on. The first, right? This is the notion of maximal elements. This is in fact 1.2 of the chapter. Maximal elements and choice sets. Okay. So what is a maximal element? Definition. Right? A max element or maximal element of S under R. You have to tell me two things. You have to tell me which set and which preference relation, right? Is X when, right? It is not true when it is not true that there exists Y belongs to S such that Y be X. Be very clear about this, right? Sorry, this will be like this here. So X is a maximal element of S under R if you look at all the other elements of S, then YPX cannot be true. There does not exist any such element. So there is no element of S which is preferred to X, right? This is called a maximal element, right? Now, there are many such X's. Maybe there's no such X, but the set of maximal elements, right, is denoted by MS, right? This is the set of maximal elements. And well, one thing you have to understand here is that there may be some element Y, right, which cannot be compared to X, right? So Y, not Y are X and not X. Right? This is not a problem for X. X can still be a maximal element, right? Even if nothing can be compared. As long as nothing is strictly better than X, we have X as a member of N. Okay. The next notion, which is very similar and many might get confused between this and that of maximal elements, is that of a best element. Definition. Best element of S under R. What is this, right? Is X when, right, for all Y belongs to S, right? For all Y belongs to S, X R Y, right? So every element of S, including X itself, X is at least as good as. So say there's a set A, B, C, right? And A R A, A R B, B R C. Then A is a best element. And the set of best elements, right, is called the choice set. Right? It is denoted by choice. C, the set, the relation. These are very basic definitions, right? And two comments are made here in the book. The first, of course, is that the choice set, right, is a subset of the maximal set. Prove this lemma. Let's call it a lemma. I don't think it's given as a lemma in the book, but we can call it one. The choice set of S under R is a subset of the maximal set. Right? How do we say this? Well, we can prove it very basically. I don't think this is a proof which merits any time, so I will keep it for you to do. But it's very simple, really. Just use the definition of P, right? Then use the definition of C to show that any element of C has to belong to M, because if X is an element of C, there cannot be any other element which is strictly preferable. Right? It is a very simple. So this is one basic comment. The second comment is the first comment. The second comment is M or F or C, maybe empty. There's no reason for them not to be empty, unless right, may be empty unless we make certain assumptions about R. Unless we assume some things about R, which we will see just in a moment's time when they cannot be empty. Okay, very well. All right, so now we will do the last part of this video. This does not end the chapter. I know I said I want to do one chapter in one video, but the first chapter is rather long, so I don't think we can cover it in one video. So we will do till 1.3 now, and then we will do 1.4, 5, and 6 in the next video. Quasi orders. This is quasi orders. Now, if you have read the book, you will know that a quasi ordering is a relation R, right? Which is reflexive and transitive, right? So these are two properties which we study. If these two properties hold for R, then R is a quasi ordering. Right? Now, we will see certain properties of quasi orderings. Right? So if R is a quasi ordering, then we will see that certain results hold. And of course, all of this. So certain results which we will look at. Lemma. I will prove only one part of this lemma, but this lemma is called the II, EI, IP, EP lemma. You will find this in the book. The format of this is very simple. I'll do the PI lemma. These can be proved by yourself at home. The book has the proofs in any case. What is this lemma? For a quasi ordering. For a quasi X, I, Y and Y, I, Z implies X, I, Z. This is called the II lemma because we have an I here, resulting in a transitive I here. This is also called II transitivity. So let's prove this, right? The others are very will have similar. So X, I, Y implies XR, YRX, YRZ. Sorry, YRX. Yeah. YIZ implies YRZ and CRY. Right? So from this and this, right, because of course this is quasi ordering, which means it's transitive and reflexive. From these two, we have XRZ, right? And from these two, similarly, we have ZRX, so we have XI. Very simple stuff. These are the four II, PI, IP, PP levels. So PI means XPY and YIZ implies XPZ. Very basic, very intuitive, right? If X is preferred over Y and Y is equally well like this, see, obviously you sense that X should be preferred over Y. You can see the rest of the lemmas here in the book. Very basic stuff. I don't think I need to prove the other lemmas at this point. Now let's look at one more lemma. These are results which we are assembling, so to speak, in the first few chapters. This is like an armory that we will use later on to prove more and more powerful results. But these lemmas are by itself quite interesting. The way in which we may do these proofs are also important to understand for later on. Anyway, so what is this lemma? Any finite quasi-ordered set has at least one maximum element. So just to remind you, finite set. So, right? So the set is given like this. It's quasi-ordered, so it's reflexive and transitive. Max element. What is a max element? A max element is one which is not a max element is such that there's no other element in the set which you strictly prefer. The role and the proof is very simple. Right? And this proof is done using construction. It's an interesting type of proof you may not have encountered before. So the set has these elements. Put A1 is equal to X. Now, right, A2 will be equal to A1. Right? Sorry, A2 will be equal to X2 if X2 be A1. So if X2 is strictly preferred over A1 or X1, we will put A2 is equal to X2. Otherwise, A2 is equal. Right? And in general, we have Aj plus 1 is equal to Xj plus 1 if Xj plus 1 be Aj. Otherwise, Aj plus 1 is equal to the same as the one. We will continue like this and finally we'll get an An. Right? An must be maximum. An, right? An must be maximum. Intuitively, this should be clear to you because at every stage, if it's preferred, we are changing the element. If it's not preferred, then it remains the same. So we are putting it through a test, so to speak. Now, right now, the book leaves it here. Right? Let me try to prove why An must be maximum. Right? So I hope you tried to prove that An must be maximum. We can prove this fact now. It's not given in the book, but I think it still merits a proof here. Okay. So we begin with the fact, okay, that Aj plus 1 are Aj for all J. Why is this true? Because if Aj plus 1 is equal to Aj, then by reflexivity, right? Otherwise, Aj plus 1 is equal to A when Xj plus 1 are Aj, which of course implies that Aj plus 1 is equal to Xj plus 1 are Aj. So we begin with this fact. Aj plus 1 are Aj. Now, to prove that Aj is maximum, right? Suppose it is not. Suppose An is not maximum. Right? Therefore, there exists Xk right? Such that xk belongs to the set, we call it S, and xk p a n, right? This is the very definition of maximal element that we're using. Now, an r, an plus 1, sorry, an minus 1, an minus 1 r, an minus 2, dot dot dot, an, sorry, a, just a second. If we go on like this, we get ak plus 1 r ak. Now using transitivity, by transitivity of quasi, we have an r ak. Right? Now, if ak is equal to xk, okay, let's do it this way. Right? If ak, okay, we'll continue this to also say this, right? So by transitivity, an r ak minus 1. Now, to complete the argument, this implies that xk p ak minus 1, right? By pi or p, right? You can check this, which implies that ak is equal to xk. But anr ak is also true, right? Which implies xkp xk cannot be true, right? So we are done. And so an is maximal, and we have proved our lemma, which is that a finite quasi ordered set must have at least one choice element. And this particular type of proof is quite common with finite sets, even in consumer choice theory, and we'll see it later on. So we will prove one more result and leave two for you to do or to check from the book. You can treat this as check yourself. This is a check yourself lemma because it's really very simple, which is that if R is reflexive, then xpy, if and only if the set containing only x is equal to the choice set when we choose from the set x comma y using the binary equation. This is very simple. Intuitively speaking, R is reflexive, x is preferred to y, so the choice set must have only x because x is strictly preferred over y, right? And so yrx cannot be true, so xry must be true here because xpy, and yrx is not true. So xry and xrx is true because R is reflexive, and we are done. Actually, this is not even, I think we are done already. You don't even need to check it. It's a very basic lemma. The next lemma which we can look at is the last lemma we will prove in this video. Is for a quasi ordering R S comma R is non-empty, right? Implies C of S comma R is equal to the maximal set S comma R. Now, we will use standard set theory techniques here. We already know that C is a subset of M. We show that M has to be a subset of C. Right? Standard set theory technique. So let Z belong to M, S comma, right? And X belong to C of S comma, right? X exists since C is not empty. Okay. Now, since Z belongs to MSR, it means that there does not exist any Y such that Y is Z. Now, that also holds for this particular element, X. Right? So, we can say that not X Z, right? Because X also belongs to S. So, it has to hold for all elements, and X is one, right? So, not X is Z, right? But XRZ must be true since X belongs to the choice set, right? So XRZ and not XZ obviously implies X and Z, right? Basic, very, very basic stuff. X is at least as good as Z, but X is not strictly better than Z. So it must be equally good as Z in simple language. Now, since XIZ, okay, so we have okay. Now, take Y belongs to S. XRY, since X belongs to C. But ZIX, like ZRX. So using transitivity, we can naturally get ZRY. But Y was an arbitrary element of S. So Z must belong to C, S comma R. Therefore, M is a subset of C. Right? Of course, note here that, I mean, the astute viewer might notice that I assume that such an element Z exists. Right? And the astute viewer might ask, how can we assume? How can we say that M is not empty? We know C is not empty. How can we say M is not empty and assume that Z belongs to M? That is very simply because C is not empty, and C is a subset of M, so M cannot be empty either, right? So that is a very interesting lemma which we'll find useful later on. The last lemma, which we will not prove because the proof is rather involved and not very illuminating, is that for a quasi-ordered set S ordered by R, right? Set a finite set. Right? It's a finite quasi-ordered set using R. For all x comma y belongs to, sorry, for all x comma y, if x comma y belongs to M implies xi y, if this condition is true, then it is equivalent to say that C of S comma R is equal to M. The proof is quite simple, but it is rather lengthy and not the sort of proof which is going to be useful for us going forward. So you may check it out from the book, page number 58. Right? So thank you very much. This was the first part of the first chapter's video. We will be coming back to you with the second half of the chapter, starting with subrelations compatibility, and we move on to rational choice and certain other topics. Thank you very much. Hope to see you soon in the next video.